Let's take a look at an example of solving a trigonometric equation like the one we have here. 3 times the sine of 2x plus 7 equals 1. So in this problem, we're going to find all the solutions of this equation, and then we're going to find just the smallest positive solution of this equation. Let's start by finding all solutions. And we're going to use a little trick that sometimes makes it a little bit easier to deal with equations like this. Just to clean up the notation, we're going to temporarily introduce another symbol to represent the argument of the trig function here. So I'm using theta to represent 2x plus 7. That way I can write my equation as 3 sine of theta equals 1, which is a little bit easier to understand. We can go another step and write this as sine of theta equals 1/3. And so basically I want to find the solutions of this equation to start with, values of theta that make this true. And then I can use that to find the values of x that make the original equation true. All right, so to start by trying to understand what the solutions of sine of theta equals 1/3 should be, let's take a look at a graph of the sine function. Here's a really rough graph of the function sine of theta. Notice we have a theta y-axis here. So when I want to solve an equation like sine of theta equals 1/3, what I'm really doing is finding all of the theta values where the graph of sine of theta intersects the line that's at a height of 1/3. One of the tools we have at our disposal for solving this kind of equation is the inverse sine function, or the arcsine function. So for example, we could look at the theta value given by sine inverse of 1/3. And that's a solution of the equation sine of theta equals 1/3, but it's not the only solution. It's this one right here. It's the smallest theta value that satisfies the equation. But there are lots of theta values that satisfy this equation. Remember, sine is a periodic function. Sine of theta has a period of 2 pi. That means if we add 2 pi to the input, we're going to get the same output. So we're actually going to find this solution. This point is 2 pi units to the right of the first point we found. We could add another 2 pi to get another solution, or we could add a negative 2 pi to get this solution. So in fact, we could add any multiple of 2 pi to get a solution. So one way of expressing that is to say that theta could be sine inverse of 1/3 plus 2 pi times k, where k is any integer, positive, negative, or 0. But that's still not all of the solutions. Notice we skipped some. For example, we skipped this one right here. How can we find the value of this solution? Well, now you want to use the symmetry of the sine function. Notice that this y-intercept on the graph of y equals sine theta, that occurs at the value pi. So this solution right here is the same distance from pi that this solution is from the y-axis, but it's to the left of theta equals pi. So we can actually find this solution by letting theta be pi minus sine inverse of 1/3. And again, we can add multiples of 2 pi to that to find the other solutions. So we can add 2 pi times k. Again, k can be any integer. And together, from these two formulas, we are expressing all of the solutions of our equation, sine of theta equals 1/3. So let's go back now to trying to solve our original equation. We can say that we have one family of solutions of the form theta equals sine inverse of 1/3 plus multiples of 2 pi. But then theta was our shorthand for 2x plus 7. So we're really saying that 2x plus 7 equals sine inverse of 1/3 plus multiples of 2 pi. And I want to solve for x, so I'm going to isolate x here algebraically. I can subtract 7 from both sides. I'm going to write this as negative 7 plus inverse sine of a third plus multiples of 2 pi, and then divide both sides by 2 and get negative 7 plus inverse sine of a third plus multiples of 2 pi, all divided by 2. This formula gives us one family of solutions for the original equation. And then remember, there was another family of solutions for theta. Those were the ones of the form theta equals pi minus sine inverse of a third plus multiples of 2 pi. So if we do the same algebra we just did here, I'm going to jump to the end. You end up with x values of the form negative 7 plus pi minus sine inverse of a third plus multiples of 2 pi, all divided by 2. That's our second family of solutions, and together these two formulas give us all of the exact solutions for our original equation. Now there was one more thing I wanted to do with this example, and that was to find the smallest positive solution of the equation. And that might not be as obvious as it seems at first. We have to do a little bit of work to decide which solution is the smallest positive one. What we have to do here is plug in values for k to get a grip on how large these x values are from each formula. For example, if we plug in 0 for k into the first family of solutions, we end up with an x value that's approximately negative 3.33. That's clearly not a positive solution, so it's not the one we're looking for. Let's see what happens if we plug in a 1. You can check this on a calculator. Make sure you're in radian mode, of course. If you plug in 1 for k into the first family of solutions, we still get a negative value for x. And if we plug in a 2, we finally get a positive solution of approximately 2.95. But that may not be the smallest positive solution. Let's take a look at the other family of solutions and see what happens. If I plug k equals 0 into that, I end up with an x value that's approximately negative 2.10. If I try k equal to 1, I end up with an x value that's approximately 1.04. And just for good measure, we'll see what happens when we plug in k equals 2. That gives us an x value of approximately 4.19. So it turns out that the smallest x value that solved this equation was actually this one, the x value that's approximately 1.04. The exact x value there is what we get when we plug a 1 into the second family of solutions. So the smallest positive solution is x equal to negative 7 plus pi minus sine inverse of a third plus 2 pi times 1. I'm plugging in a 1 for k, so I'm not going to write times 1. All divided by 2. That's the exact value of the smallest positive solution, and it's approximately 1.04. So that was it for this example. I just want to finish with a few quick remarks about how to solve similar equations. When we were trying to solve something which could be written in the form sine of theta equals, let's call it a, we used two families of solutions. Sine inverse of a plus multiples of 2 pi. And we also used pi minus sine inverse of a plus multiples of 2 pi. Now, what if we want to solve an equation that can be expressed in the form cosine of theta equals a? Well, in that case, you start similarly. Your first solution will be cosine inverse of a, and you add multiples of the period 2 pi. But then your second solution will take advantage of the symmetry of the cosine function, but it's not the same as the symmetry of the sine function. We don't actually want pi minus cosine inverse. We actually just want negative cosine inverse of a to help us generate our second family of solutions. Finally, if we want to solve something that can be written in the form tangent inverse, or tangent of theta equals a, we can use the inverse tangent function. And then we want to add multiples of the period of tangent, but tangent doesn't have a period of 2 pi, it has a period of pi. So we just need to add multiples of that. And tangent has a slightly different graph than these others, than sine and cosine, in that you only need one formula to express the family of solutions that capture all solutions for tangent of theta equals a.